Okay, so we're just going to back up a little bit just to make sure I'm not skipping anything and talk about what we've should have learned about Riemann sums and also the area that's beneath a curve. Um, it says here a definite integral represents the area under the curve of a function. We've talked about the idea of integration, and that's what we're working towards. So when we're able to find this definite integral, it is the area under the curve of a function. Okay. How is that different from a Riemann sum? It says a Riemann sum gives us an approximation. Okay, the Riemann sum is just an approximation of that area. And we know that often with the AP questions, they'll make a distinction between exact and approximation. So if we're just looking at a Riemann sum, it's an approximation. When we do the definite integral, it is the exact area beneath the curve. Okay, it says imagine that we could create an infinite number of partitions or rectangles in a Riemann sum. The approximation would get closer to the actual area as the subintervals in the Riemann sum increased. We can't take a Riemann sum with infinite rectangles, n equals infinity, in our summation because infinity isn't a real number. However, we already know that the way that we're able to look at what would happen if we could get infinitely many rectangles is to use the limit process, right? So it says, however, if R of n represents the right Riemann sum approximation with n subdivisions, we can use limits when we want to take something to infinity. Then the exact value of the definite integral can be shown by, okay, this is not just the Riemann sum, but also the limit of it, okay? So small distinctions. Riemann sum is an approximation. If we look at the limit of the Riemann sum as n approaches infinity, that is the definition of the definite integral. And those two things, just to be consistent, I'm going to back this up and put this in the yellow highlight as well. These two things are exact because the definite integral is the limit as n approaches infinity. And it doesn't have to be for the right sum. It could be the left sum, the mid sum, any of those sums. But when we apply that limit process, then we get an exact value. All right, so we looked at how we do this. This is just a review summary of how we get to that right hand sum. Of course, right here is where we're going to determine the width of our intervals or the rectangles. So we do b minus a divided by n. Okay, if we don't know what n is, then we just leave it there. We can use the limit to drive in towards infinity. And of course, all of these y values are the value of the function at these particular points. Okay, and so when we put it all together here, what we're finding is the area beneath the curve. The way that that's represented in our integral notation is we're looking at the integral from a to b of f of x dx. Okay, and in our limit notation, it's equal to the limit as n approaches infinity of the summation of k equals 1 to n of f of x sub k times delta x, where of course delta x is that b minus a divided by n. Okay, and we had some practice with that, and we're going to get some more practice with that. All right, the definite integral of a continuous function f of x over the interval ab, denoted by the integral from a to b of f of x dx, is the limit of a Riemann sum as the number of subdivisions approaches infinity. Okay, and I think we've already got that part. Let's talk about though these x sub k's. Okay, x sub k is going to be a. A is our left endpoint of the interval where we're trying to find the area. So the leftmost endpoint plus delta x times k. Okay, k is going to be represent the different rectangles, the first rectangle, the second rectangle, the third, fourth, fifth rectangle, all the way up to the nth rectangle. Okay, we're going to multiply that by the width of the rectangle. Okay, and this just lets us know what these x values are. After this, of course, we're going to need to take these x values and actually plug them into the function whose area we're trying to find. All right, so here we have this example. It says given the graph of the function f of x equals 1/2 x squared plus 1 on the interval from 0 to 4, this exact area can be represented using definite integral notation. All right, and you see the notation there. Okay, we're going to write the definite integral as the Riemann sum. Okay, and we're going to do this. Um, I think at some point, I think we did this one already. At some point, it said something about 8 rectangles, but we're just going to go ahead and do it for the n rectangles, okay? Because that's where we want to get. So remember, somewhere in our notes, a few slides back or a few pages back, we had a pretty nice summary of the steps that we needed to go through to find or to set up this whole summation notation for the area. So first step, we want to find out what delta x is. Second step, find out what the right end point of each rectangle is going to be, if that's the method that we're using. And I think we already talked about, it really doesn't matter whether we do left end point or right end point. Okay, then we're going to find the area of the kth rectangle. So it's going to be the width, delta x, times f of x, which is the height of the function at the kth x value that we're looking at. Okay, and then we're going to put that all together as the Riemann sum. Okay, and they give us some instructions. If we decide to do left Riemann sum, we can just change the index. Oops. We can change the index from k equals 1 to k equals 0, and that's going to get us to look at those left endpoints. So left endpoint versus right endpoint is just a small adjustment. All right, so we're trying to write the definite integral as the limit. So the first thing I want to do is note that the integral goes from 0 to 4. Okay, and so I can figure out my delta x. Delta x is equal to b minus a over n, or 4 minus 0 over n. So our delta x is 4 over n. Okay, we've got that. All right, so now that we have that, the next thing we want to look at is what our k's, our x sub k's look like. All right, and so we saw that x sub k is going to be a plus delta x times k. All right, and so for us, a is 0. Delta x we just found above is 4 over n, and we're going to multiply that by k. Or we could say 4k over n. All right, so we're going to put in the process that we'll be looking at would put in 1 for k, and then it's going to put in 2 for k, and 3 for k, and 4 for k, all the way up to n for k. We're going to have n of these rectangles. Okay, now that we've got that, okay, we know that the area of any individual rectangle is going to be delta x times f of x sub k. All right, so our function is 1 over x squared plus 1. So we got 4k over n. I'm sorry, let's go back. 4 over n. That's our delta x. And then we want f of 4k over n, because we just defined above that our x sub k's are 4k over n. So I want to look at f of those x sub k's. All right. Our f function we said was 1/2 x squared um, plus 1. So we get 4 over n times 1/2 4k over n squared plus 1. All right. This is f of x sub k. All right. For our particular f function. Okay. And so now that we have that, that's just one rectangle. What we want to do is add up all of those areas. So I can do that by saying that my total area, and at this point it's approximately equal to the summation of k equals 1 to n, okay, of all of these areas. So 4 over n times, we can go ahead and simplify this f of x sub k. It's going to give me 16k squared over 2n squared. All right, plus 1. Okay, and I'm going to check that just to be sure, because I don't have you all here to check me. But we got 16k squared over n squared and then times 2 plus 1. Okay, so that's the approximation. What makes this exact, what makes this equal to the integral from 0 to 4 of 1/2 x squared plus 1 dx is when we apply the limit as n approaches infinity of the summation of k equals 1 to n of 4 over n times 16k squared over 2n squared plus 1. Okay, so what they wanted us to do in this problem is write the definite integral as a right Riemann sum. They said with 8 subdivisions, equal subdivisions, but I did it with n equal subdivisions because that's what we're going to want to do. So yes, we went a step beyond, but this is our ultimate goal. So yes, this is what we want to do. Okay. All right, now let's look at the next example where they're still stepping us through this process. And again, I think we covered this part, but I just wanted to make sure that I didn't skip anything. So here they ask us to use our calculator to evaluate the definite integral. So let's take a look at our calculator. Okay, so on the calculator, we were able to do this integration by going to the math menu. Okay, and I believe we went to option 9 where we want to do integration. And if your calculator is updated, then it pretty much sets up the integration for us just the way that we need it. So I'll just fill this in just the way that it is in our problem. Okay, we want to integrate from 1 to 2. And we're integrating x plus 1 dx. Okay, and again, it asks us about dx because when you get to calculus 3 and you're doing double integration, triple integration even, you can integrate with respect to different variables. So the calculator is asking us about that. And so we go ahead and hit enter and we get 2.5. Okay. If we need it for whatever reason to convert that to a fraction, then we could hit math, fraction, and enter, and it'll give us 5/2. Okay. Now what we want to do is write the Riemann sum of this integral. Okay, so first of all, the width of our rectangle is going to be 2 minus 1 divided by n, or just 1 over n. That's our delta x. Okay, the left endpoint of the interval is 1, and we're going to add to that delta x times k. So that's going to be 1 over n times k, or 1 plus k over n. All right, so those are our x values. Now I need to figure out what my f values are. And so they look like f of 1 plus k over n. Okay, well, f, our function, is x plus 1. So if this is my x, then I'm going to take x and add 1 to it. And so we get 2 plus k over n. Okay. And so the corresponding Riemann sum with limit, okay, is going to be the limit as n approaches infinity, okay, of 1 over n times the summation of k equals 1 to n. Okay, and here we're doing the area, right? So um, the 1 over n is our width. We can pull that outside of the summation because the summation is going to be changing things where we have a k, not those things where we have an n. And we'll talk a little bit more about summarizing this or simplifying this a little bit later. But we've got the summation for k equals 1 to n of 2 plus k over n. All right. Um, I'm just thinking about questions that you might have. And this 1 over n is our delta x. So this is the delta x times f of x sub k, except we've done the summation of all of that. So we could say summation. Remember, for the area, to get the area of each rectangle, they all have the same width delta x. And we're able to factor that delta x out. For us, delta x was 1 over n, right? And so that's why we were able to factor it out right here. That is our delta x. And the only thing that we had left was the f of x sub k. Okay, so now it says evaluate the limit of your Riemann sum on a calculator. What is the answer? So let's take a look at how we'll be able to do that. Okay, on our calculator, we're going to go over here to y equals, and we're going to use summation notation, which our calculator has, to look at a pattern to evaluate the limit. All right, so we're going to see how this thing, since we're talking about the limit as n approaches infinity, we're going to put in larger and larger and larger values for n to see if we can detect any pattern or any behavior for this entire process. All right, so that's to say that the limit piece we're going to kind of do manually. So what we really want to look at is the summation. Okay, so I've got 1 over n, and we'll just use the same variables that, well, actually, let's do 1 over x. All right, so instead of using n on our calculator, we'll use x, all right, because we'll be able to change that easily. And then we're going to look at the summation. So if we go to math, and I believe option 0, that's our summation. It pretty much sets the summation up just the way that we've been using it. So I'm going to do alpha k as my index for summation. We're going to go from 1 to n, or we're using x in place of n. All right, and we've got 2 plus k over n, or 2 plus, we'll do k over x. All right, so we've put the function in. It's y1 for us, so let's get out of here. And now we're going to do alpha trace. We want to get y1. Okay, and remember I've used the variable x in place of n in this case. So I want to see what happens if we use 10 rectangles. Okay, all right, we get 2.55. All right, if I do 100 rectangles. All right, so you see I'm increasing the number of rectangles. All right, and it looks like we got 2.505. All right, I think we did this in class and put in some numbers that kind of choked the calculator, so we won't go too far, but let's just go ahead and try maybe 300. All right, so I'll just change 100 to 300. And you can see we're getting closer and closer and closer to a value of 2.5, which is actually what we found when we did the definite integration on the calculator. We got 5/2 or 2.5. So we can see that these two things are the same.